Amazing, there are actually a few people here. I thought you'd be off doing more rewarding activities, but maybe not. Okay. So let's start with any burning questions about the project or anything like that. At this point, we have a couple of autograder runs. The second one should have all the features that we're actually going to test in the real runs. And if you notice serious problems that ought to be addressed, then now is the time to bring them up, preferably with bug submits. I remind you that there will be a test next week. I believe the TAs will probably follow their previous practice of having extended office hours, but I don't see anyone here to ask, so I'll find out about that. And of course, I will have ordinary office hours, but I'm usually around, so you can dig me up too. So you haven't had time to think of a question? Okay, fine. In that case, we'll go back to the main material, which was object-oriented programming, or object method dispatching specifically, and how it's done. So, I didn't get around to putting that wonderful example in here. So with Python, original Python, or full Python, real Python, official Python, you have this dynamic approach where basically every object contains a dictionary. And a new dictionary for each object, in principle. If you don't find the thing you're looking for in the dictionary, you look in the dictionary for your classes, for your superclasses, and if you don't find them there, then it's an error. If you assign into an attribute of an object, when that attribute does not currently exist, then it is created. And when you assign into, as here, when you assign to the object in the class a.x, then in full Python, that object is available, or that value is visible then from all of the objects, all the instances of A, previous and current instances and instances you create thereafter, is visible to them if they have not already assigned if they haven't made their own copy of the instance variable internally. So this is all interesting, but as you can imagine, and it's very flexible. I mean, you can add, if you can have your instances of some type look completely different from each other. An instance can be tailored. A given instance, not just a class, not just a subtype, but the instance itself can have as many new fields as you want. Instances can be completely incompatible with each other. Now there will be some that have an attribute, some that don't. So of course, any idea of static checking is, forget it. You can't do that kind of thing. So, and in fact, in the purest form, we don't even bother with classes. You just start with an instance variable. You just start with an object, and you insert into it whatever you want, and you have some operation like clone, for example, that gives you, once if you want classes, if you want sort of some template from which you stamp out objects, no problem. You just make one exemplar object, and then you stamp out instances by using clone. So there's a language called self that does that, as a matter of fact. Very interesting. So that is the fully dynamic approach. That's the absolutely fully dynamic approach, where you don't even have classes, and it's it's another instance of the duck typing principle. That if you make something, and if it responds to the right messages, then fine, and that's as close as you get to actually having typing. So, and here is the implementation, which we've gone through by now. So all objects are carrying around their dynamic type, but that dynamic type is used basically to tell you to to respond to the what is my type operation or function, and also to look up default values for things that aren't present in the object. Okay, so that's what you get, and it's dynamic, and that's nice, and it's simple, it's flexible, the implementation is easy. That is to say, for the implementer, it's easy. It doesn't perform all that well, of course. You have lookups you're doing all the time. You have space overheads, and you can't do any static checking at all, to speak of, in the general case anyway. So, yes?
So if you were to overwrite a method that already existed in the class, any objects that existed in that method, any instances that method override would not get the new.
No. In full Python, they would. So the question is, what happens if we go back to A here? If I assign into if I were to assign a new function instead of, if I said def f self and so forth, return 42, if I were to replace that with, this is actually illegal, isn't it? Because I can't have a def on the same line as it's not a simple statement. Oh, my bad. If I were to replace that with, say, g, a function g, so I said capital A dot f equals my new function g, then in fact any method, any instance variable that had not made its own copy of f by assigning into itself.f would now have that new function as the method. So yes, very dynamic, extremely dynamic. All right, so and now maybe it's pure prejudice that, there are two things going on here. First of all, there are people who don't like the idea of losing an order of magnitude performance or more in order to have nice general features. They don't need that. And then there's also this question of static checking. The point I've heard from various programmers is that, when you write something like this, when you write a class, you have some intention for what a.f is, what method it is, or at least what its signature is. And good practice, if you're trying to be able to use this code and have it maintained, is that get documented somehow and perhaps enforced so that you can count on it. So, and it's also nice to know in advance, to have some automatic warning without having to wonder whether you've tested it, whether everything's going to work. So, for those reasons, I think in general, the community would prefer to have some kind of static structure in which you can do a little more analysis and you have a little more enforcement. Okay, so we start with a simple scheme. I'm just calling straight single inheritance with dynamic typing. So, in this scheme, we have each class has a fixed set of methods and instance variables. You can't add new ones at execution time. And each method has a fixed definition. For that matter, each instance has a fixed definition also, although it may have that as an object, as a container, or variable. And that variable, however, may contain different values at different times. And in this scheme, we are allowed to inherit from one superclass, sort of like what we're doing in the project, in fact, very much like what we're doing in the project. But otherwise, we're going to keep all the typing dynamic. So in this scheme, there's just the we don't have static types for things. We just keep the classes have fixed structure once they're set up, and instances have fixed structure. So this is how it works in, for example, Smalltalk. So everything has a dynamic type, but the classes of methods are generally not changed at runtime. Oh yes, I mean, in an interactive environment, there are ways of redefining things, and so you can set a new method definition and so forth, but that's sort of outside the language. Right. So this looks like, this is what Java would be, or kind of like what Java would be if you didn't have to declare the types of variables and parameters and instance variables. So here is an implementation. So the big savings here is that that objects don't have to carry around copies of function pointers. They don't have to carry around dictionaries. Instead, since the structure of these objects is fixed, we can do something like this. So here we have a simple thing where we have a class B that inherits from A. A has these two methods f and g and an instance variable x. B has two methods f and h, so f overrides A's method, h is a new method, and it has its own instance variable. And we create two instances, A and B, of these things respectively. And here's what they look like. So in this implementation scheme, an instance of A looks like this, with a pointer at the top. It has a pointer to its class, or some runtime information that corresponds to its class, which is called various things in various languages. In C++, it's called a virtual table pointer. And that's a name that's actually often used. And then it has a space for its instance variables. B has the same thing. It has a pointer to its class, and it has space for instance variables too. The two instance variables it has, the one that it inherits from A, and the new one that it adds. Now, the important thing here is that the initial part of B, that is these first two fields, have exactly the same structure as those two fields in A. That's the crucial point here, or one of the two crucial points here. All right, so then what do the classes look like? Well, the classes then look like this. They contain a pointer to their supertype, plus the bodies, or pointers to the bodies for all the methods, plus some. Now, in this particular instance, I have something that gives information about where the instance variable is. That isn't strictly speaking necessary, but if you're going to have dynamic typing, you sort of need something like that. So we have something that tells us what the instance variable is, and I'm just going to imagine in this particular language that this value here that we assign inside the class definition is some sort of an initial value that we keep around inside the class. So this is kind of the way that we're doing it. This is sort of the class variable that contains the initial value and and gets copied into here. Not quite the way Python does it, but then this is not Python. Okay, so this is nice. And it gives us all the information. So evidently, the strategy here, let's see, do I say that on the next slide? All right. So the strategy here is, if I want to access, for example, the method f, then I can look at I can go to the class on an object B. I just go to the class of that object. I look to see whether it has a definition of that method in its body here. If it doesn't, then I go up to its superclass and I ask there. And so that's very familiar. I mean, sounds kind of like environment diagrams all over again, except in a slightly different context and a slightly different purpose. But it's really very much the same thing. If I ask for x, I'll be told, well, there's no x down here in B. Oh, I see. This is x is one of these inherited instance variables. You will find it at location 4 inside U. So these are, we're assuming each one of these is 4 bytes, so that means that instance variable x is right here, starts right here. Instance variable y at 8 starts right here, the second one. So all the information, so I leave to you the implementation of this thing, but all of the information is stored in the class, and it's a simple matter to access it. And the thing about this is that the only things that we need to store in the objects, aside that is from the pointer to the class, are the things that can be modified, the things that can be changed in that object, which are the instance variables. And it may be a little bit faster than accessing the fully dynamic thing because the dictionaries, the class things have fixed size at any given time. But again, because of this dynamic typing, we don't have any static type checking. And we do still have to do, and because we don't have any static type checking, we do still have to do some looking up of the method names. So, but this is a step, this is one step along the road. And in order for this to work, we have to have a language in which it's not allowed that you insert new instance variables. Although actually there is a way around that. I could use this scheme and still be able to insert new instance variables into a class and have it, or into an instance. Well, no, into a class, that is, and have it work. How would I do that? This is actually an easy question disguised as a subtle one. Yeah. Yeah, I could just extend the class array as I go along. Now the problem with that is that if, for example, I add a new instance variable, all the existing objects will not have that instance variable. So if I create a bunch of A's, and then I create a new instance variable, add it to the class A, and then I ask for that instance variable in one of the old objects, well, the value, the new offset in the class will be wrong, so or it will point to garbage in the old object. So what can I do about that? Think daringly. What can I do about that? What?
You could have classes have pointers to like the structure of their variables instead of having classes.
A pointer to the pattern of their instance variables. And what would you do with this?
So if you wanted to add a new instance variable to a class, all you have to do is follow the pointer, like a heap or something, and then add a new variable to that add.
Well, that's fine. I mean, what you're telling me how I can modify the class dynamically, and that's great. But what I'm saying is I've done. You got this? Friday, 6 p.m., food. There's something about doing some work too, but I don't know if you guys are interested in that. So this is I've created A1, which is an A. Now I add a new field, A dot Z equals 2. Now it's no problem if I say now A2 equals A, and then say a2.z, what on earth is this? a2.z, that's obviously no problem. But what happens when I say a1.z? A1 will contain just one instance variable. It won't have the z instance variable. So how am I going to make sense of this? Yeah.
Have each instance sort of keep track of how many instance variables it knows about, and if the offset is too great, say, hold on just a sec, let me reload the class and figure out what these other instance variables are.
Okay, so we could have a distributed overhead in which every time you access an instance variable, you also have this additional check to see whether this instance variable is actually in this particular object. That works, of course, if you also had an operation of replacing an instance variable or deleting an instance variable, which would not increase the number of instance variables. That particular check might not work. Yeah, so that works too. The audacious way to do this, and something like this has been done occasionally, is to simply keep track, as you create new objects, to keep track of all of the objects that you've created. And then if anyone changes a class, which is assumed to be a rare operation, just go back through all of the objects that exist and modify them. Which sounds, boy, that sounds horrendous, you know. I mean, it's a lot of work. But again, since changing an element of a class is a weird thing to do anyway, who cares? In fact, the instances in which you might do that are probably when you're working interactively on the system, and you've got this program and you're interacting with it and dynamically building the program the way Lisp and Smalltalk programmers do. And you just change something in a class, and at that point the system has to go and essentially redo all the objects. Well, you know, I mean, you're a human being. You're working at this glacially slow pace compared to the computer. So, you know, what's a couple of seconds or a couple of milliseconds or whatever compared to the amount of time that it takes you to move your finger to the next key? So it's a potentially viable approach. Okay, so that's nice. Now, so let's see what happens when we add another language feature, static typing. So now everything will have its own static type. And so single inheritance, that's Java without interfaces. And that means that at any given time, for any access like x.w, the compiler, because of static typing, the compiler will know some supertype. He will know the supertype of x, of x's value, specifically, or the supertype of x's values type, specifically the supertype that contains the definition of w. It knows that at compile time. And then all it has to do is to make sure that whenever you override a method, you give it whenever you override something or subtype something, that information in the supertype remains valid, no matter for all subtypes. So that means that all instance variables for subtypes of something, an instance variable in all subtypes of some class have to be in exactly the same location. Methods for all subtypes of a class, methods that are inherited, that are shared by all of those, have to have exactly the same signature. And as long as that's true, you can make some nice guarantees. Okay, so what we're going to do is create new virtual tables that look like this. I've changed the terminology from old slide. So from class to virtual table. But really in C++, I think we could call, for example, where they use this technique, we could call the virtual table the runtime equivalent of the class, and it wouldn't be too far wrong. So here's how it works. Now our class F, we have these 4 bodies, one for F, one for G, one overriding for F, and a new function H. So now the virtual tables over here no longer have to contain any information about the instance variables. They just have to contain some information about the methods. Specifically, the stuff they have to contain are the bodies of the methods, or pointers to the bodies of the methods. That's all the information you need to keep in the class. And now, what's going to happen is if I ask for a.x, for example, or b.x, either one, I will know that x has to be at this location right here in every single A. It has to be at exactly that location. So I may not know which subtype of A I've got my hands on, but I know that they all put the variable x at exactly the same location. And all the subtypes of B put the variable y at exactly the same location, namely there. Okay, so that's good. Now, when I want to look something up, when I want to call a method of A or B, well, it's the same thing. I can look it up. I know that in this case, I know that all subtypes of A have a pointer to their F body and their G body at this location, at these relative locations from the beginning of the virtual table. So all subtypes of A have a virtual table that starts with with pointers to the bodies of F and G. All of them. Because there is single, and why can you do this? Why can you do that? Why is this going to work? Well, because there's single inheritance, which means that you can always put the methods, you can always put the methods in the virtual table after the methods of your parent, and it will work. There will be no conflicts. And likewise for instance variables in the instances. So this is really neat. And at that point, because of this structure, because of all the static typing, the compiler knows first the location of every instance variable in any variable, regardless of whether it knows precisely its type. It has enough information to know where the instance variables are, and it has enough information to know where in the virtual table to look. It knows where the virtual table is because it's always pointed to from this pointer at the very beginning of an object, and it knows that when it reaches into the virtual table, it may not know whether it has a pointer to an A or a pointer to a B, but it does know that if it wants to call the G method, it's always going to look at this location in the virtual table. And that's how you do it. So here we have, so in order to get the effect of overriding F, we simply arrange that the F slot in B's virtual table contain the new body, contain the overriding body. To inherit something from F, we simply set up the subtypes table to contain the inherited method, a pointer to the inherited method. So both A and B share a pointer to body 2, and so forth. So that means that a method call requires no lookup at all. All you have to do is dereference pointer to get the pointer to the virtual table, dereference pointer to get the pointer to the method, to get the body of the method, call the method. That's all you need to do to do a method call. And you know that, and that method, that's going to work even if you store an instance of B inside a variable whose static type is A. It's still going to work. That's a nice little implementation technique. And It would be nice if we could just leave it there, but as you know, things then started to get complicated. So now the interesting stuff follows, or the really interesting stuff follows. So at this point, it's a reasonable time to leave this on the cliff and take a break. Questions on this? Is this clear? I hope this implementation technique should not be terribly obscure, but it does have its subtleties. And in particular, you should understand, in studying this, you should make sure you understand, first of all, why all of these things are, why the compiler knows all of these things, what properties of the language, or how does the fact that there is single inheritance make all of this possible, make it possible for the compiler to know all of this stuff statically. It all fits together very nicely. All right, fine, let's take a break. All right, let's pick this up again. So here's the picture. Java introduces these interface thingies, so I can implement an interface C and a function f that relies on that interface. The interface basically says, I am the interface to things that have a method called f. I have left off all the stuff about types and so forth, all the boring stuff. So I have this method called f, no parameters. And you can actually compile that interface and this function here in the absence of anything else. I can also define two classes, A and B, without knowing anything about the interface or anything else, and you can just compile them and use them. And then I can extend, noticing that both of them happen to have a function f, I can extend both A and B to make these new classes that are the same except they implement C. Or maybe they have some overridings in addition, I don't know. But in any case, they implement C. So the question is, how does this work? Because the problem, you see, is that if we use naively the method that we did before for implementing class A and B, then it's unlikely that f will end up in the same place in the virtual table in both of those, because, so it would seem, because class B has these extra methods G and H, and the way I've written it in such a way as to suggest that the entry for f is going to occur after the entries for G and H. So that means that wherever, if I have a pointer to something that's an A2 or a B2, A2 and B2 are supposed to put in their virtual tables, they're supposed to put the method f at the same place as in A and B, respectively. That means that when I do this call here in C, y.f paren, since that could come from either an A2 or a B2 or some other type that isn't on this slide, what is the fixed location of f that I go to in order to figure out what to call? In other words, how can this work? So that's basically the issue here. That's basically the monkey wrench that gets thrown into our former scheme when you say, oh, let's have interface types. Let's have interfaces. Let's see. Now, the implementation that I actually like, although it has its downside, is brute force. You say, oh, the heck with it. I'm going to put off deciding where to put the methods in their tables. I'm going to put that off until the compiler has available, the compiler or the linker or something, has available all of the source files that are going to go into the final program. And when that happens, I will just make sure that in every table whatsoever that's used, every virtual table, the entry for the function f with no parameters goes at exactly the same location in the table. So I just do a global, allocation of slots, of methods to slots. Now we can get a little bit of compression by not worrying about if we know that there are no common interfaces to two different types. In other words, two types will never be brought together by an interface the way they were on the previous slide. Then it doesn't matter. They can have independent orderings of methods. But the easy thing is to just say we'll just choose a new slot for each different method signature. So that means that the virtual table for a C will now be compatible with the virtual table for A or B, for A or B, and also for A2 and B2. And therefore, when you're compiling code right here, when the compiler is generating code here, it may not know the dynamic type of Y, but it knows where the F method in Y is going to be. So it can just use that method. So this is it's simple. It works very nicely. It doesn't require any special, it requires no overhead at runtime once things get started. But of course it does have these problems. First of all, the virtual tables will now get considerably bigger because they have provisions for all these methods that aren't in the class but are in some other class. And that means that we have to. And we also have to have all of this information, this global information about all the classes before we can actually lay out the virtual tables. Now, actually, that's not so difficult for a linker or something at about the time the linker operates, because basically the only thing you're going to change in the programs are you're going to figure out what all the little constants are for when the compiler reaches into the virtual table for Y and pulls out F, it has to know what the offset is. So if that's determined at link time, well, that's fine, because it just means you have this assembly language instruction where I do the base offset address of getting this function. I just change the offset and everything's fine. That's not too difficult, the sort of thing that linkers can do. But if I want to do dynamic linking, which is, by the way, a feature of Java, if I want to be able to load a new class at execution time, then things might get a little dicey. So, for example, imagine that I've got this situation, and I figured out where all the classes are going to be, and then at runtime, during execution time, I suddenly decide, oh, I need this new class. I need a new class D that has a method F in it. And so what am I going to do? Well, it just means it's not such a bad problem. It just means that when you lay out the virtual table for D, you've got to be careful to, what am I doing here? When you lay out the virtual table for that new type, you've just got to make sure that you you choose the right slots for methods. So it's not so terrible. If you were trying to optimize the tables by taking advantage of methods of classes that don't overlap, that are never linked by objects, well, then the introduction of a new class could cause trouble, and you might have to do something. You might have to do something drastic. So all in all, the big downside of this is the big downside of this, I think, is the fact that the size of all the methods, method tables, increases. So the obvious thing now, as an engineer, you mustn't stop there. You mustn't say, oh, the size increases, therefore this is bad. That's not good. You can't do that, because as engineers, we're always choosing between things that are many different things that are each bad for its own reason, and we're trying to weigh this. So we have to always ask the question, in a case like this, how bad? Compared to what I'm going to show you on the next slide, how bad? Right? So I don't know. You can look at C++. You might ask yourself this question in, say, Java. How many different classes in any particular program? How many different classes tend to get loaded simultaneously? Let's suppose 500. Right? And in each class, how many methods, or what is the total number of distinct method signatures, that is names and distinct slots we might need in a virtual table? What's that? Oh, I don't know. I'd say 1,000. Right? I don't know, in any given program. Okay, 500 times 1,000, that's 500,000. Entry to 500,000 bytes, times 4 is 2 megabytes of virtual tables, and the 1,000 classes, or 500 classes, 1,000 methods, that's a pretty big program. Oh, it's April. It's the first Wednesday of April already. How nice. 2 megabytes of extra code space. What's 2 megabytes here, 2 megabytes there? Pretty soon you're talking about real storage, but you have to do it quite a bit. So maybe that trade-off is not so bad. I mean, that's sort of the upper end. I don't know if that's terribly bad. Since I've been dealing with some multi-hundred megabyte executables recently, I don't tend to think of that as so bad. Okay, so anyway, that's method 1, and now, next time we'll get into the way it's done in actual implementations, and you'll see how complicated it can get.